Okay, shall we get started? Okay, yeah. Hi, everyone. My name is Yuan, and I'm a co-founder of XCamp. I'm leading teaching and technology. And today, we are very happy to have our beloved teacher, Max, to talk about Gold level live solution of the December USACO competition. And Max is the ICPC World finalist, and also he has been teaching at XCamp for a long time. He's the ICPC World finalist, and he's very good at explaining very complex concepts and algorithms. To give a sense of Max class teaching quality, on the right side is a list of scores. These are the students. Sorry, these are the scores of the students in his class who got the least scores in the December Gold level competition. I think majority of the class will pass Gold this time. Hopefully it's not 800 this time. So let's go to the next page. Yeah, so then I will hand over to Max to talk about the Gold level problem tutorials. And yeah, Max is all yours now.
All right. Thank you, Yuan. Yep. So I'll just go ahead and jump straight into the problems. So this table here shows a brief overview of some of the topics that might be kind of used for these problems and what classes might learn them in. But let's just go ahead and jump into the solutions. So the first problem was called flight routes, and I'm going to go ahead and jump over to my whiteboard to explain. So what the problem asks is it gives us essentially a graph of these different essentially it gives us a graph of n vertices. Say n is less than or equal to 750. And basically what they give us is they give us a matrix. The problem gives us a matrix. I'll say, or for every pair ij.
Max, just to sorry to interrupt. You probably want to show the whiteboard.
Oh, sorry. Yes. Let me share. Yeah. So everyone can see that? Yeah. Yeah. So it gives us, let's see, it gives us a matrix of I through J. And what it tells us is that, and it gives us the parity. We are given the parity of the number of paths from I to J. So parity is like even or odd, right? So that's what this is a parity. When I say parity, I mean even or odd. And now our task is we want to determine the total number of edges. We want to count the total number of edges, like direct edges in this graph. And everything was with I is less than J. So there's yeah. So how should we approach this problem? Well, when we look at this condition of parity, and we try to analyze the number of paths, let's say we fix a pair ij, then a path from I to J, it can be a direct path like I going to J, or it can go through some intermediate vertices. So it might go to some intermediate vertex K, K1, it might go to some intermediate vertex K2, and so on, so forth, and eventually it reaches J, right? That is the other possibility. And so let's focus. So this kind of motivates us to kind of maybe look at first, maybe let's first look at like a simple case. Let's say I and I plus 1, the immediate pair. Because this graph is only has edges from I to J with I less than J. So if we're considering paths between I to I plus 1, there can't be the only possible path is like directly from I to I plus 1. There's no possible because there is no intermediate vertex that this could possibly go through. And you're not allowed to go like backwards and then back over here. That's not allowed per the constraints of the problem. So this kind of motivates us to start looking at first like the close ones, like I to I plus 1, because for those, if the parity is 1, we instantly know that it has to be an edge, right? Because if the parity something like parity equals 1, that implies there's an edge, and parity equals 0, there would be no edge for a simple case like this. And then if we figured out all the distance one pairs first, we figured out like I to I plus one. Now next it makes sense to look at like I to I plus two. And then from I to I plus two, it's either like from I to I plus two, we have like either like I directly to I plus two, or we have like I through some intermediate vertex, say I plus one, and then to I plus two. But with the intermediate case, these are just like these are kind of like the previous case that we just mentioned, right? Like I to I plus one, I plus one, I plus two. These are distance one cases, which you've already computed before. And so in general, this is starting to look like some sort of dynamic programming, in particular a range dynamic programming. And so let's analyze this now in full. So in total, suppose we have for any ij, I'm going to process these in increasing order of j minus I. What I'm going to do is essentially from I to j, we're going to first consider the case where there is an intermediate vertex. So in that case, we're going to iterate on k. So we're going to go ahead and iterate on k. And to avoid overcounting, we're going to assume that the k is the second vertex on the path. And so now, if there's an edge, from like let's say from I to k, then we have the parity. Then the parity of the number of paths from k to j will all contribute to the total parity of the parity of k to j will contribute to the total parity of the paths from I to j, right? So from a counting perspective, we're basically trying to count all the intermediate paths or all the paths that go from I to j through some intermediate vertex k, where k is the second vertex on that path. And so if there's an edge from I to k, then we can take all the paths from k to j, and that all contributes to the parity. And so basically, we take for every single k where the edge exists, we take all the parity of kj, we XOR them all together because parity basically flips. And then at the end, if the total we end up with, if the total parity we end up with is not the same as like the input matrix that we got, the input matrix ij, that implies that there needs to be one more path, or we need one more. That implies that um we also need a path from I to j directly without any intermediate vertices. So if this whole pair does not match, that implies that we also need an edge from I to j. So in total, we just we basically compute this for all the pairs ij in increasing order of j minus I, increasing order of j minus I, because by doing it that way, all the previous like the internal ranges like I to k and k to j will already be computed, and then we simply check. And for this, by doing this, we're able to determine for each pair ij there should be an edge between them. And this entire algorithm will work in, let's see, so there are two for loops on I and j, and then a third for loop on k, each up to n. So this is an O of n cubed algorithm. And we remember that n was 750, so 750 cubed. That is a bit much, but we can divide this by roughly by 6, because if you think about all the triplets that we iterate over, we only iterate over I, which is less than k, which is less than j. So you can kind of divide by a factor of 6 for the amount of iteration that we do, because each triplet is only counted once and not like not like each permutation. So this will run fast enough. All right. So that is the first problem. Like I said, I can take any questions before I move on to the second one. Cool. All right, let's move to the second problem then. The second problem